In last sessions we have seen some results about Cauchy sequences, convergence sequences, monotone Bourne sequences. So let me just recall what we have done. So there are 4 classes of sequences: Cauchy, convergent, monotone, bounded. So what we have seen is very easily that every Cauchy sequence, every convergence sequence is bounded, every Cauchy sequence is bounded, and every convergence sequence is Cauchy. That's all we have seen. Every convergence sequence has to be bounded. If I am looking to reach anywhere near being convergent, I should start with being bounded. That is that should be the starting place. So, okay. So the question is simple. Suppose I started a bounded sequence. How far can I go towards looking for convergence? So bounded. If it is monotone, then we already have this convergence. If it is not monotone, or if it is not Cauchy, how far can I reach towards being convergent, towards this sequence being convergent? Now we know we have examples for which bounded sequences are not convergent, so that's not what we are expecting. So let us keep this in mind. So let us keep this question in mind and then see how far we can reach. So let us recall what we have done for Cauchy sequence being convergent in that proof. So we introduced notion of what is called lim sup, right? Lim sup, lim inf. So we mentioned about this notion of lim inf. So by definition, this is a limit of some sequence. That sequence is defined as the following: Bn is equal to infimum of Ak, this k greater than or equal to n. So this is how we have defined this notion of. This gave a sequence. For each n, we are collecting the sequence that starts at that n. We have taken infimum of that set, the measure of the sequence, then we call it as Bn. So this gives a sequence. For each n, we have an element in R. So this gives a sequence. We have realized that this is it increasing or decreasing? Is infimum sequence, is it increasing or decreasing? So whatever it is, we realize it is a monotone sequence, and because an is bounded, this is also a bounded sequence. So by that theorem, this converges to some element. That element is what we are calling as lim inf of an. Similarly, lim sup of an is again a limit of some sequence. And what is the sequence? The sequence is we denoted by Cn, that is supremum of Ak, k greater than or equal to n. So this is also same thing. For each n, we are assigning an element in R. However, we are assigning, we fix some element n. Then we consider the sequence that starts at n. The sequence Ak, that k is equal to n, that starts from n. Then we have realized, then we have considered the supremum of that, because the sequence is bounded sequence, this will be a bounded set. So I am taking a supremum of that bounded set, that I am writing as Cn. Then we realize that Cn is a increasing or decreasing sequence. Check in the previous lecture whether it is increasing or decreasing sequence. But you should at least remember it is a monotone sequence. This is we are starting with a bounded sequence, we got a monotone sequence, this is also bounded. So this converges to something, and that something is what we are calling a lim sup of an. So last time we gave just the definition, but we didn't really write any example. Let us do some example now. Consider the sequence an, that is defined as 2 for odd, 1 for even elements of n. Now, so for convenience, let us write down the sequence as the following. This is 1, 2, 1, 2, 1, 2, so on. So if I am writing this as A, what should be the sequence B? This B1 should be defined in the following. B1 is equal to infimum of, I have to start from here, take this whole sequence, look at its image, then take infimum. What is the image of this sequence? 1 comma 2. What is the infimum? 1. Very nice. So this B1 is 1. Very good. What is B2? B2 is infimum of a sequence that starts at 2. We are ignoring the first element that starts at 2. So what is the image of this sequence that starts at 2? Again 1 comma 2, that is equal to 1. Nice. So what is B3? Infimum of the same thing. You have to remove the first 2 elements, start the sequence from this point, take the image is 1 comma 2, infimum is equal to 1. I mean I can do it for B4, B5, B6 also, but everything you might have realized already that everything will be same thing as 1. So what we have seen is this Bn is equal to 1 for every n belongs to n. So I will write down the B here 1, 1, 1, 1, 1, 1, so on. We already know that this sequence is a constant sequence that converges. It converges to 1, right? Nice. Then let us now compute lim sup. So now what we want? We want this sequence C, C1, C2, so on. What is C1? C1 is equal to not infimum, supremum. Supremum of, I have to look at the sequence A, I have to look at this sequence starting from 1, consider this sequence, look at its image, take supremum. This sequence image is simply 1 comma 2, let me write down that 1 comma 2, supremum is 2. For C2 again I have to start it here, take the corresponding sequence, take the image and the supremum. If I start at 2, the image of this is simply again 1 comma 2, supremum is 2. And you also know now that Cn is equal to 2 for all n belongs to n. So what do we have now? That this sequence, the supremum sequence is actually the constant sequence 2, 2, 2, 2, 2, dot, dot, dot. This is a constant sequence that converges to 2. This we have seen already before, that constant sequences converges to the same element. So one need to observe the following here. See, even though A is not a convergent sequence, we have got 2 sequences out of that A which are convergent. See, this is I am only writing this, I am only doing this example here. This we have already observed in the previous session, lim sup, lim inf are sequences that converges. So what is the special observation here now? I mean, why do you have to think of this example? One thing to notice is the following. If you observe that these 2 sequences has some elements in common. What is that? This one is common. So one should realize that the image of this sequence, which is just singleton 1, is contained in image of this sequence, which is 1 comma 2. So now what do we have? Let me write down that. So given a sequence A is equal to An, we have a sequence B, Bn such that this B of n is contained in A of n, which is again a subset of R. Okay. So a sequence B is said to be nice with respect to the sequence A if this happens. If it is more nicer than just this, that we are calling as subsequence. What is the being more nicer? We will see now. See, this notion of subsequence should not be very surprising for you. I mean, this should not be surprising at all. Why? Because the same idea you have seen in case of subgroup, vector subspace, or any sub thing. So let me do the following. Given a group G, a subset H is said to be subgroup if something happens. Given a vector space V, a subset W is said to be vector subspace if something happens. So similarly, if I want to call something as a subsequence, at least the image should be contained in this image. Yeah, that is the first thing that it should satisfy at least. Now, this is not just a subset, subgroup. If you already know, subgroup is not just a subset, it satisfies some condition. What is the condition? That the structure on here, it is induced from structure on G. Let me write down the relevant part in case of subsequences. So what do we have here now? Image of A contains image of B. So let me write down this N to R as B, N to R as A. Now see, this condition says the image of B is contained in image of A. Okay. So for a sequence B to be called as a subsequence of A, first condition is this, that the image should be contained in this. Second condition is, whenever we have some situation here, we say these two are nice if there is a map that fill the diagram. So what does it mean? It means that there is a map F from N to N such that A compose F is equal to B. One more thing to observe is, we are not planning to allow all maps from N to N. I mean, we want this map to be order preserving in the following sense, that if M is less than N, then f of M should be less than f of N. If there is a map A from N to N such that A compose F is equal to B, then we call B to be subsequence of A. This is what a subsequence notion is. So now what we have seen is, in the previous example, that we are starting with a bounded sequence that is not convergent, but we have a subsequence. See, this is subsequence, and I mean we can actually write down what is F here. So there F is N to N, N is mapped to N plus 1. So this is a sequence. 1 should go to 3, 2 should go to 5. So what we are doing is we are collecting all the alternating elements, 3, 5, so on. So this has come here 1, this has come here 2, something will come here as this. So this says this B is a subsequence of A. So now let me write down what we have observed here. So if An is a bounded sequence, An is a bounded sequence, then we have observed that there exists a subsequence such that Bn is convergent. This is what we have observed here, right? That An is this, An is this, A is this sequence, B is this sequence. We have seen that B is a subsequence of A and B converges to some element. That is what you have written here. Maybe I will just pull it down, right? This is correct, right? That for every bounded sequence there exists a subsequence such that Bn is convergent sequence. How do we know that? We have seen this example that for this bounded sequence there is a subsequence that is convergent. So this should be the case for every sequence An. Yeah. Yes, no, think about it. I gave one example of bounded sequence for which there was a convergent subsequence. Now I am saying the same idea should work for any bounded sequence. I wanted to give as an exercise, but I mean I already gave a justification why I am guessing that this is true. So this theorem, okay, this result goes by the name of Bolzano-Weierstrass theorem. You should give it a try. Just because it is a theorem, it does not mean it is supposed to be difficult. It is very easy. Believe me, you will be able to do it. Maybe I will just give some rough idea how to do, then you can try. Okay. So AN is a bounded sequence. Nice. So that I am starting with that AN is a bounded sequence. Now we want to prove that there is a subsequence such that it is convergent. Nice. See, thinking about a subsequence, maybe I don't even know where to start. We should think of a map, right, from F from N to N, then consider A compose F into R, and then see that this is a convergent sequence. That is fine. So instead of using this approach, let us go back and check bounded sequence was convergent if it is a monotone sequence. So if I assume it is monotone sequence, this is already convergent sequence. So I can simply take this to be identity map, and this A compose F is simply same thing as A. This is convergent sequence. So the only question is when it is not a monotone sequence. If AN is not monotone, then there is a small problem. I don't even know where to start, right. If it is monotone, then I can simply take this F to be identity map. A compose F is same thing as A, monotone, bounded is convergent, so AN is convergent, so this is convergent. So I am seeing a sequence and subsequence of itself. A group is a subgroup of itself, the vector space is a subspace of itself. So one can just conclude that it is a for this AN there is subsequence that converges to something. Now suppose it is not monotone, I don't know what to do. If you don't know what to do, first thing to do is write down what it means. What does it mean to say that AN is not monotone? Do we know what is monotone means first of all? Forget about not monotone. Do we know what is this monotone means? Let us write down this first. This will write later maybe. So AN is monotone means what? I have already said before that monotoneness means something should be very nice from the very beginning. Let me write down this sequence as A1, A2, ... So let us assume that it is a monotone increasing sequence. I said monotone here, it should be increasing or decreasing, let us do increasing. So this is a monotone increasing sequence. So what does it mean? That A1 less than or equal to A2 less than or equal to A3 less than or equal to so on. So what to observe here? For each n and any other element m such that m is greater than n, then AN is less than AM. Let us write down that. So for each n belongs to n, something happens. What is it? If m is greater than n, then AM is greater than or equal to AN. Right? Whatever I have written here, I am writing in English. So for each n belongs to n, if you take 2, let me take n to be 2, then what does it say? For every m greater than 2, AM is greater than or equal to AN. You can take 3, 3 is greater than 2, A3 is greater than or equal to A2, this is fine. You can take another element, so this is what it means. For each n, this is the condition. Now the question is, if it is not monotone, what does it mean? It means something should go wrong at some n. For positive thing, we need to have for every n belongs to n, something should happen. For not monotone, what do you think we should have? At some n, something should go wrong. So there may be some n belongs to n such that something is wrong, and there may be some n such that that is actually correct, that this satisfies this condition. So there may be some elements of n for which it is true, for which this is true, there may be some elements of n for which this is not true, right. Those are the only two options, right. Because we assume it is not monotone, there is a chance that something it is true, something is not true. So let us estimate the damage, how much damage has occurred, or if you want to hear nice things, let us estimate the deviation. the deviation of an to be monotone increasing. The deviation of this sequence from being monotone increasing. So, how do we calculate that? We collect all elements n belongs to n such that the whatever you have written here, we want this to be true. So, right, as I said, the set n is now split into two parts. One is elements of n for which this does not happen, elements of n for which this happens. These are the only two possibilities. So, let me write down that. So, let me actually write down what is this. So, n belongs to n such that for m greater than n we have am is greater than or equal to an. This is one set where this is nice. Let us write down not nice, so nice set also. So, n belongs to n such that this does not happen, which means there exists a m belongs to n with m greater than n, but am is less than an. So, this n is union of these two sets, this set and this set, right. As I said, if an is monotone increasing, then this does not happen, this does not appear anywhere. For every n belongs to n and m greater than n, this is true always, but because an is not monotone increasing, there should be some place where it is wrong. That wrongness is what I am writing as this. So, n is a union of two sets, and this says how nice it is, how near is this sequence being from monotone increasing. This says how far. I mean, this is actually just complement of this, but still this seems to be supporting for our cause, whatever we are fighting for. This person is supporting us. So, let us work with this. So, E is equal to n belongs to n such that am is greater than an for every m greater than n. This is the situation. Now, let us see the damage from the point of view of E. If this is very bad, in the sense that there is no place where it is monotone increasing, then E should be empty set, right. E should be an empty set. I mean, there are no elements for which this satisfy. For each stage there should be something that is going wrong, right. So, in particular 1 which is an element of n is not an element of E. Right? E is an empty set. So, if I take 1 belongs to n, this is not here. What does it mean? It means there exists a m belongs to n such that m is greater than 1 and am is less than or equal to a1. Here n is playing the role of 1 here. So, if you observe the similarity m greater than n, m greater than 1, this is not true for there exists m belongs to n such that m is greater than 1, but this is the case. Now, just for convenience, let us write down this as n2 and this as n1. So, this one I am replacing by n1, this m I am replacing by n2. So, what do we have? We have a n2 is less than or equal to a n1. Very nice. Now, take this element, starting at 1 we got some element for which this is the case. Let us start at here now, instead of starting at some other place, let us start here. This is also not an element of E, right. E is empty set. So, this cannot be an element of E. So, n2 is not an element of E. So, this should go wrong, which means what? Again there exists a m greater than n2 such that am is less than or equal to an2. Let me write down that there exists m belongs to n such that m is greater than n2, but am is less than or equal to an2. Again I am replacing this m by n3. It is only to remind that I am doing at the second step. At the second step I am getting some element that I am writing as n3, and this also n3. If you observe, an3 is less than an2, an2 is less than an1, which implies an3 is less than or equal to an1. This should suggest to you already that maybe if we proceed like this forever, at least for some time, we will get a decreasing sequence. Right? One can do the same thing for n3 now. For this n3, there exists a n4 such that n4 is greater than n3, but an4 is less than or equal to an3. This will continue forever. So, now what do we have is n1 less than n2 less than n3 less than n4, so on. For these elements we have an1, an2, an3, an4, so on. So, now what do we have? If I assume that E is an empty set starting at n1, I got increasing sequence in n, I got the elements of n in this, and we got a decreasing subsequence of A. This is a decreasing subsequence. And now what f should I write here? F is mapped from n to n, right? N to n. So, what should I write here? The element 1 is mapped to n1, right? That is what I have done here, no? 1 is equal to n1. I am saying this is actually what I am writing here. 1 is mapped to n1. Now, where should I map to? 2 is mapped to n2, 3 is mapped to n3, k is mapped to nk. You do this forever, you get a map from n to n such that A compose f of an element k is A f of k, that is equal to A of nk. What is A of nk? Whatever we are writing here, this A subscript nk, right? That is what it is. So, this sequence whatever we are writing here is subsequence of A by this f. So, if E is an empty set, then we get a decreasing subsequence of A. Now, let us assume that E is non-empty but finite. We will increase the complexity of degree 1 for each step. Previously it was empty, now it is non-empty but finite. Now how do I start it? I do not even know how to start. Again, if you do not know how to start at a different case, let us just go back and check how did you start for the first case. If E was empty, I took the element 1, because E is empty, 1 is not element of E, but because E is non-empty, the 1 may be an element of E. So, let us not take 1, let us take 2. 2 is not an element of E or element of E. How do you know that? All we know is that E is a finite set. So, 2 may be an element of E. So, I cannot apply that here. What about 3, 4, 5, 6? Because E is a finite set, after some finite items, we will reach a stage where I have an element n belongs to n such that this n is not an element of E. E is a finite set, n is not a finite set. So, after a certain stage, I get an element n belongs to n such that n is not element of E. Or you can take the maximum of the set E, maximum of E, and add 1, that element whatever I have erased here, that element is not an element of E. So instead of starting at 1, let us start at n1. n1 is the some element, whatever n I am writing here, that is what I am writing as n1 here. n1 is element of n, that is not an element of E, because E is finite. I can get a n1 like this. Again n1 not an element of E, so something should go wrong here. Let me erase this part. n1 is not an element of E, something should go wrong here. There exists n2 belongs to n, this and this. I can proceed further. And get this. So there is not much difference between E being empty set or E being finite set. If E is empty set, I can start at 1. If he is a non-empty set but finite, I know that there is element n1 such that n1 is an element of n but not element of E. Because E is finite, I can take the maximum of that set E, add 1, that will be outside E, that is not an element of E, and I can apply the same thing, that whatever I have done before, I can do the same thing here also. So 2 cases are covered. E is empty set is covered, E is finite, non-empty is covered. Let us now increase the complexity by asking that E is infinite. I do not like this word infinite. I mean to say E is unbounded set. E is a unbounded subset of n. E subset of n is unbounded. In the usual terminology, this only means it is a infinite set. Now what do? We will write down the elements of E in some order, that any 2 elements of n, I can tell whether 1 is less than or equal to 2. So taking the order of n into consideration, let us write down elements of E in an increasing order. So n1 less than n2 less than n3, so on. So these are elements of E, taking the order of n into consideration, we have written down in this way. Now n1 is an element of E. What does it says? It says for every m greater than n1, am is greater than an1. So for this n1, what do we have? The an1 is less than or equal to am for every m greater than n1. Now instead of looking for arbitrary element m with this property, look here, we already have an element n2 that is greater than n1. So this is true for all m greater than or equal to n1. In particular, for m is equal to n2, this is true. We will erase this, not relevant now. Now we will apply this idea for this n2. Why? n2 is also an element of E. For n2, we have this property an2 less than or equal to am for every m greater than or equal to n2. I think you know what to do now. This is true for all m greater than or equal to n2, n3 is greater than n2. So one can replace this and put n3 and erase this. We will proceed this further. So we will use the elements mentioned here only, because all these elements are elements of E. So one can apply this idea for all this n1 into n3 so on. So what do we get? an1 less than or equal to an2, an2 less than or equal to an3. What do you think an4 should be? Where do you think it should be? Here. an5 here, so on. Again, now how do I write down the map F? F was a map from n to n. What do I write down? write 1 to n1. E was unbounded. So, we have taken the minimum element of that. So, that is n1. Now, we are looking for elements of E that are greater than n1, then I am taking the least element of that. So, 2 is n2, 3 is n3 and so on. So, with this function, what about A compose f of k, that is equal to A of f of k, A of nk, that is equal to A nk. I mean, this is not really anything serious, but so what do we have? We have a sequence an1 starting at an1, we have an increasing sequence, and because of this, this is a subsequence of the sequence A, subsequence of this sequence A that we have started with. So, if A is bounded, what we have done is the following: this set E measures the deviation or damage for An to be monotone, non-increasing. Then we have said that there are some options for E. E can be empty set, non-empty set, non-empty, but so much. For empty set we have already seen. We can start with we can start at this place being 1. For non-empty, we cannot start at 1 here. So, what we have done, we have taken a maximum element of that set E, add 1, that element is not element of E. So, we will start it there. If E is unbounded, what we have done is, we have written down the elements of E in increasing order and then apply that every element of this is an element of E. So, I get this idea, I get so this is the case for every m greater than n1, in particular for n2 greater than n1, this is the case. Now, apply that the same idea for this element n2. N2 is an element of E. So, for every m greater than n2, we have this condition. In particular, for n3, we have this condition. One can do the same thing again and again and get a increasing sequence, that is a subsequence of A. So, An is bounded, implies there exists a subsequence that is convergent. Where does the convergence situation came? I only proved that it is increasing, right? Or it is decreasing? Monotone decreasing, monotone increasing, bounded sequences are convergent. That is what we have seen before. So, starting with the bounded sequence, what we got is a monotone increasing or decreasing sequence. In both cases, they are convergent. So, we get a subsequence that is convergent. So, that is all. Is that all? I assumed that An is not monotone increasing, it can be monotone decreasing. Then whatever I have done, I cannot use that idea. So, what do we do? Again, let us assume that An is not monotone decreasing. Now, instead of asking for niceness of, instead of asking for a deviation of An being monotone increasing, ask for the deviation of An being monotone decreasing. So, again we can consider this set, instead of greater than we get less than, and one can again do the same thing. If A is empty and empty or finite, we get some sequence here increasing, we will get increasing sequence, not decreasing. If A is unbounded, we get a decreasing sequence. If you are starting that An is not a monotone decreasing sequence, we get a decreasing sequence, right. So, see, whatever I have said, increasing decreasing may not be correct, you think about it. For this not increasing, we got this idea. For decreasing, we might have to change slightly here and there. Who will do that? I think you know who will do that. Yeah, finish the proof, and that's all. So now we have we have the result that says every bounded sequence has a convergent subsequence, and this goes by the name of, as I said, Bolzano-Weierstrass theorem. You do not have to remember the name of the theorem, but you should remember what we have proved. Names are, it is okay to forget the names. Okay, nice. Now what do I do? If I do not know how to proceed further, let us go back and check where did we stop. So before thinking about Bolzano-Weierstrass theorem, which means we did not know the name of the theorem, but we have realized something is happening. Starting at a bounded sequence, we have seen that there is a subsequence such that it is convergent. Where did you see this? We have seen for this example. What is example? A. This is a bounded sequence. It is not convergent. And then we have seen an example of a subsequence B that is convergent. So just immediately after seeing this, we have concluded that it is true for all such sequences, and luckily we were able to prove that it is correct. So now we are happy. Let us not be very happy. Let us see if we have missed anything special. Observe, yes, for this sequence, if it is bounded, we got a sequence that is convergent to 1. Is this the only sequence that we considered? What about this sequence? This is the subsequence, this is the convergent. But unfortunately, this is 2, this is 1, 1 is not equal to 2. Given a sequence, given this sequence which is not convergent, we got 2 subsequences that converges to different points. Right? We will write down that first. What we have seen there, we will write down that. So given a sequence En that is not convergent, see whenever I write En, I mean it is bounded, right? Without boundedness I do not even know how to proceed. So En is bounded but not convergent. What we have seen is there are sequences Bn and Cn such that Bn converges to B, not B, Bn converges to element P, Cn converges to Q such that P is not equal to Q. And this is true. This is true. This is always true. Always true. Is it always true? We know only one example of this, right? An was 2 1 2 1 2 1. This was sequence 1 1 1 1 that converges to 1. This was sequence 2 2 2 2 2 that converges to 2. 1 is not equal to 2, so we have this. So there is a sufficient justification for this being true, but this is a general sequence that may not even have 1 or 2 as convergence. There may not be any sequence that converges to 1 or 2. We only know about 1 and 2. But I am saying this is still true, and again, who will do this? That is all for this session. That is all for sequences of real numbers. So we have done sufficient theory for sequence of real numbers. From next session we will see about functions between subsets of real numbers, and yeah, that is all. These 10 lectures are extremely important to proceed further. So take some time, watch all the videos, and then convince yourself that you understand most of it. And let me assure this, the result, that ideas or whatever I have used in these 10 lectures, this will keep on repeating. No surprising things will happen, that I can assure you. Whatever happened for sequences series, this will keep on repeating, maybe up to some small correction. But once you understand the idea behind these sequences and all, none of the others will be surprising for you, and you will be able to appreciate it in a better way. So watch all the 10 videos, make sure you understand all of these, then we will see the functions part. So next session we will see about functions between set of real numbers. That is all.